Alright friends, welcome back. In this video I'd like to go ahead and take a look at the last section of Chapter 5 that we'll discuss, which is Section 5.5, and we'll take a first day for this in this video, and specifically what we want to talk about is a couple of different questions where we are applying exponentials and logarithms to solve application problems. And so we're going to take a look at a couple of different word problems here in this lesson, and the key theme throughout all of them is that we're basically going to be taking a formula involving an exponential or a logarithm, and we're going to be using our algebra skills to isolate a certain variable in that formula. And so one of the things that we're really going to need to make sure that you guys have under your belt is how you can transform from exponential language to logarithm language, which is just something I wrote a little bit of a mapping for at the top of our notes here. So make sure that you're clear on that whole looping around translation trick that we've been taking a look at in the past couple of videos before we continue on with this one. So just getting some practice with the skills we're going to need for the rest of the problems here in this video. We have example 1 where they're basically going to give us the compound interest formula, and we're going to have to take this formula and solve for a particular variable in that formula. And so you can see that we need to solve for p, and then after that we need to take the formula and solve for t separately. So let's go ahead and start over their formula here. So the compound interest formula again goes in the following way. It goes the amount of money that you end up with, A, that's going to be equal to the amount of money that you start with, P, that's your principal amount, times 1 plus your rate over N to the power of N times T. Pardon me. And so what we need to do here is we need to go through and use our algebra skills to get P isolated. And so P in the formula, of course, is right here. And so if we're asking ourselves how we might go ahead and isolate this variable, we have to go ahead and ask ourselves that very same question that we've always asked ourselves whenever we isolate any variable in an equation, which is what operations are being done to that variable, right? What operations involve this variable P right here? You notice that P does not involve, adding anything to P or subtracting anything from P. There's not anything being divided from P, or there's no exponents on P or anything like that. The only operation that P is involved with here is it's being multiplied times this quantity that you see in the parentheses that's being raised to the exponent. And so we need to undo that operation if we're going to try to isolate P. So because it's multiplication, we can see here, we're going to basically undo multiplication with a quick division, and we are going to go ahead and divide both sides by this quantity being multiplied times P in this equation. And so I'm going to go ahead and divide both sides by the 1 plus r over n to the power of nt, and that will be enough to isolate P here in this formula. And the reason that we might want to do this is because we might have a particular question about a problem where we're given everything that we need to know in order to figure out what P is, and this formula will basically allow us to go ahead and plug everything that we know and be able to get that P very quickly. And so this would be P isolated in that formula right there. Now, if we wanted to go ahead and take the exact same formula and instead solve for T, we'd have to go ahead and do it in a little bit of a different way because there's different operations involving T in the formula as there were involving P. And so let's go ahead and take a look at that formula again, where now we want to focus here on this variable T, which we can see is up here in the exponent. Okay, and so what we're going to need to do is isolate that exponential first and then use our trick to convert the language to logs to get that T isolated. And so to get the exponential by itself, we can see here that P is just chilling out in front. So we're just going to go ahead and undo that multiplication times P by dividing both sides by P first, and that eliminates the P's on the right-hand side. So on the left-hand side, we have A divided by P, and that's going to be equal to the base of our exponential, which is the 1 plus r over n, and that's raised to the exponent, which is n times t. Okay, we're still trying to get t by itself, and so the way that we're going to get t is we need to get it out of the realm of that exponent. And the way that we're going to do that is we're going to convert the language over. So we're going to start off with the base, and we're going to say log with a base of 1 plus r over n of a over p is equal to n times t, okay? And so as awkward as this might look, that's exactly what we're going to need to do in order to get t out of that exponent realm here. So we're going to take a log with the base of whatever 1 plus r over n is, as awkward as that seems, and we're going to go ahead and say that the input of our log is a over p, and that is n times t. So again, the reason that this looks so awkward is because we're having to stick strictly with the variables. We don't have anything to plug in for those variables, so we don't really have any values that we can simplify using these operations as we go through to maybe make this look a little bit simpler. It's going to look complicated as we go through because we're having to keep the variables as we go, but we only have one more step here, and that's to go ahead and get t isolated by simply taking care of that multiplication by n, which we'll do by dividing both sides by n here, and then we get this nice formula that has t isolated. So again, this might be useful in questions where we want to go ahead and take all the information that we might have dealing with compound interest, and we might want to go ahead and figure out what the time is. And we could use this formula to go ahead and do that. So log base of whatever 1 plus r over n is of a over p, all divided by n, that will be the complete formula that we can use to figure out what t would be in an example like this. And so, as far as this being practical, this might be something where if you were programming an Excel spreadsheet, you might go ahead and program it so that you can have spaces where you input like the initial amount, the ending amount, and then the number of times you compound, and then this will be something that you can go ahead and combine with the rate in an Excel spreadsheet to go ahead and figure out time and calculate it quickly. But again, it's going to be using skills like this where we're isolating a specific variable in our equation we're going to need for the rest of the examples that come here in this video. So here in the next example, example 2, we can see here that we have this big table, and we've already seen that I've got some work done here already just for the sake of time in the video. And what I want to do here, it says in the directions to complete the table below, assuming that interest is compounded continuously. And so remember that we've already talked about compound interest, and anytime it says that it's compounded continuously, we know that we need a special formula for that. So that formula goes like this. The amount that you end with is going to be equal to the amount that you began with times Euler's number to the power of the rate times time. And so it's by using this formula right here that we're going to do all the different questions involved with finding all the different values in the table. And it's because they use this word continuously right here that tells us that we need to use that formula. Now here in the table, you can see here that we have a bunch of different columns, and you can see here that I've gone ahead and gone through and labeled all the 3 different examples we have to do with A, B, and C to just say that each row is a different example. And we just have to go through and fill in all the missing blanks. And so real quick, what I want to do is I want to kind of retranslate each column in terms of the different variables that are in our formula here. So the first column here has our initial amount of money, and so in the formula here, that is going to be represented by capital letter P. The next column over, it says the annual interest rate. That is going to be your R. And the only thing I want to say about the interest rate is that keep in mind in this column it's going to be presented to you as a percent. So just keep in mind when we go ahead and do the formula, we need to take this number and divide it by 100, and that's going to be the decimal number that we're going to use in place of our R value in our formula. Now the next 2 columns over ask for specific things. So the next column over asks for the amount of time it's going to take for your principal amount of money to double. So how much time is it going to take for the original amount of money that you invested to double in amount, right? So what this basically asks in terms of the formula is what is time? So what is T going to be? T is equal to what when your amount of money has doubled. So that means the amount of money that you end with, A, is going to be equal to double the amount you started with. So double P, or in other words, 2 times P. Okay, so we'll take a look at that situation here in a moment. This very last column asks us what is the ending amount of money when T is 10 years. So in terms of the formula, what is your ending amount of money, A, when T is 10 for 10 years? Okay, so it's oftentimes good to kind of go through and translate the different things that you're being asked for to make the problem as easy as possible. So I'm going to go ahead and demonstrate row A, where they're only asking us to figure out the 3rd and the 4th column, and then the work for B and C I'll go ahead and put up on the screen for you to pause the screen and read through here. So let's come over here where I got some room. And let's go ahead and write down capital A for that first row there. And again, the question that we want to ask first is how much time is it going to take for our money to double, right? We know that we have this formula. The amount that we end with is equal to the amount that we start with times Euler's number to the power of the rate times the time. But here's the thing. We know that our initial amount of money is going to be $750 in this first example. And we are interested in the amount of time it's going to take for that money to double. Okay, so if you double $750, that's going to give you $1,500. And so we're curious about the amount of time it's going to take for $750 to turn into $1,500. And so on the other side of the equation, the right-hand side, we're going to pick up with our Euler's number to the power of our rate, which they gave us in the problem. And they gave us to that as 10.5%, so we're going to divide that by 100 and call that 0.105 times the power of t. So t is what we're going to leave as our general variable here because we're trying to solve for t and figure out what that is. And now we just have an equation where we now need to go ahead and go through and isolate t in this equation to figure out what the amount of time is. And so you can see here that this involves the exact same skills as we practiced in example 1 of the video today. We just need to isolate t, so that means we need to get rid of that 750 that's out front being multiplied. So that just means we're going to go through and divide both sides by $750. And without using a calculator, we automatically are going to know that the left-hand side is actually going to be 2 because, again, we're interested in the amount of time it's going to take for it to double. And 1,500 is exactly double 750, so when we divide the two, we know we're going to get 2. So 2 is equal to Euler's number to the power of 0.105 times t. And again, we need to go through and isolate t here. And so now that we've isolated that exponential, what we now need to do is make sure to translate the language over to logarithm language so that we can get t out of the realm of that exponent here. And so if we loop around to translate the language, that's going to be the log base e, or the natural log, of 2 is equal to 0.105 times t. And of course, to get t isolated here, we just have one more step. We just need to go through and divide both sides by that decimal number 0.105. And then we can punch that into the calculator and we can get our answer pretty easily. Okay, so we'll say t is approximately equal to, we know that these decimal numbers cancel over here on the right-hand side, and so what we're just going to punch into the calculator is this right here, the natural log of 2 divided by 0.105. And so let's go ahead and go to the calculator and punch that in. So the fraction, natural log of 2 over 0.105, and that's going to be equal to this decimal number right here. Now, while we're in the calculator, I do want to make the point that if you have a calculator where you type things in left to right instead of the TI-84 here where it is able to let us type in a fraction exactly the way that it looks, you might type it in like this, right? So the natural log of 2 divided by 0.105. Now, if I were to just press enter here, it would not give me the result that it gave me in the previous line, because one of the things that you need to make sure that you do if you have one of these types of calculators is you need to make sure that you tell the calculator exactly what the input is. For that reason, we need to make sure that we go ahead and end our parentheses there before we press enter, and you can see that it gives us the exact same result. If we have left that off, then we would have been telling the calculator that the input inside of our natural log would be whatever 2 divided by that decimal number is, and you can see that we get a different value in that case. And so we just need to be a little bit careful about what we type in, but we can see that our answer here is going to be about 6.6 years, and so that is going to be the answer to this problem. Okay, so that is going to be the amount of time it's going to take for our money to double. So we'll punch that in into the table up here, and we can see that we only have one more thing that we're trying to find. Remember that we're trying to find the amount of money after 10 years, so we just need to figure out what A is in the formula when we let t be equal to 10. So let's start over with our formula here. So we have our ending amount of money is equal to our principal amount times e to the power of rate times time. We know that our principal amount is $750, so we're going to punch that in. And then for the rate, we know that that's going to be 0.105, just like before, and now we know that t is 10 because we want to figure this out for 10 years. And so this is just a straightforward application of the formula. I'm not going to take us to the calculator because I already have that value ready to go here in my notes, just for the sake of time in the video. That's going to be $2,143.24 to finish this off here. So you can see here in the table, if I go ahead and put up the work for parts B and C here, this is going to be the work to show for if you wanted to go ahead and fill in those other blanks in the table. So it looks like for part B, they wanted the interest rate and the amount of time it's going to take for your money to double. And then in part C, they wanted the initial amount, and they also wanted the interest rate in that problem. So you can see that the problem gets set up in different ways depending on what you want to find. So I invite you to go ahead and pause the screen here and maybe go ahead and take a look at parts B and C and just read through those and make sure that you're able to make sense out of what it is we set up and how we solved those equations. I'm going to go ahead and move on here to example 3 here, and it just asks us a simple question about compound interest, and I just want to make sure that we're going through and making sure that we're translating everything in terms of the formula so that we know exactly how to solve one like this. So we know that for compound interest, the formula is going to go like this. This is not continuous interest, so it's not like the last problem. It's going to be like the number 1 we did today. So that's going to be the ending amount of money is equal to our principal amount times 1 plus the rate divided by n, all to the power of n times time. And n is the number of times we compound our interest in a year. And so if we translate the question in terms of the variables in this formula, we might ask ourselves this question: what are they asking for? Well, it says here, how much money should you invest? So how much money should you invest? That is your beginning amount of money. So in terms of the variables in the formula, we might go ahead and rephrase the question as, what is P going to be in the formula if playing the role of all the other variables are the following, right? So they say at 4.5%, that is your rate. So that is going to be 0.0475 if we divide that number by 100. And then it says so that you will have $1 million. That's going to be A is equal to 1 million for your retirement in 15 years. That's T. So T is equal to 15. If the interest is compounded quarterly, okay? So if you ask yourself how many times per year is that, if it's quarterly, that's going to be 4 times. You split up the year into quarters, and it's going to be once for each one of those quarters. And so now we have everything that we need to go ahead and punch into our formula here, and then what we need to figure out is what is P going to be in this formula. That is going to be the principal amount, because they asked how much should we initially invest if we want to end up with $1 million here, and so P is going to be the variable that we're going to isolate here in this formula. Now, you might remember from example 1 earlier in this very video that we isolated P already. We said that P was just going to be equal to A divided by 1 plus R over N to the power of N times T. And so again, the reason that we did that is because now if we're interested in solving a problem like this, P is already isolated, so we don't need to do all the heavy lifting to isolate that all over again. We could just go ahead and punch in what we know and then go ahead and ask the calculator what this result is going to be equal to here. And so in terms of what we know here, we know that A is going to be 1 million. We know that 1 plus the rate was 0.0475. We know the number of times to compound is 4 because it's quarterly. And we know we have to raise this to the power of 4 times time, which is going to be 15. Okay? I'm not going to take us over to the calculator to punch all that in. Just for the sake of time in the video, I already have the result ready to go here. What you should end up with here is approximately going to be equal to this dollar amount. So that's going to be $492,449.36. So again, by doing that work that we did in example 1 here in the video, we're able to go ahead and ask this question, how much money should you invest, by going back to that formula and solving it for P, and then punching in all the things that we know so that we don't really have to do any algebra here. It's just punching in the things that we know and then going right to the calculator to get our result. So that's a pretty quick thing. In example 4, if you read through the problem here, I basically just want to do the exact same thing and just kind of translate everything in terms of the formula that we want to use. So in example 4, they're going to ask you, how long will it take? And so they're asking you for time there. So they're basically, in terms of the formula, saying, what is T, time? How long is it going to take for your money to double? Okay, and so again, phrasing that question in terms of the variables in the formula, if we're waiting for our money to double, that means that our principal amount is going to be multiplied by 2, and that is going to be our ending amount. So when we're asking for the money to double, we're basically saying the amount that we end with is going to be 2 times the amount that we began with, or 2 times our principal. It says here that the interest rate is 8.5%. Don't forget to divide that by 100. That's going to be 0.085. And then finally, it's going to say compounded annually, compounded monthly, or compounded continuously. Okay, so just real quick, when they say annually, that means just once a year. When they say monthly, that means once per month, so that means 12 times per year because there's 12 months in a year. And then for continuously, remember, that means we're using this special formula involving Euler's number over here. And so I've already done all the work for this, and you can see the different results there and how close they all match up. Again, it's just a matter of just pausing the screen, reading through the problem, making sure you understand the work that's involved and how we set these problems up and this kind of thing. If you guys have any questions over this one, feel free to send me a message, but we're just going to go ahead and move on to this last example here in the video just for the sake of time, where we're not talking about money, we're going to talk about half-life, which is going to be this concept where if you let a radioactive isotope sit on the shelf for a certain amount of time, the question is, how long will it take for that amount of isotope to decay to half of its original amount, right? That's what half-life is. And apparently for this isotope, carbon-14, the half-life for it is going to be 5,730 years. So if you have a jar of this stuff that's just sitting on the shelf for that amount of time, it's going to start from a beginning amount, like let's say maybe you started off with 12 grams in a jar. After that amount of time, it's going to decay down to half that amount, which of course is 10 grams. And so what they're going to ask us in the problem is this. If we give this jar 1,000 years to just sit on the shelf, and in that jar there's going to be an initial amount of 6 grams, how long is it going to be before it decays down to half of 6 grams, which of course is 3 grams, right? Well, they give us this nice model here, and in this model what this is QT, that is the final amount. Q0, that is the initial amount. And K is what we call the rate of decay, or the constant of decay, and T, of course, is time. So you can see that this very closely matches the interest rate formula whenever it was compounded continuously, because it involves Euler's number here. And so what we're going to go ahead and do here to solve the problem is we're basically just going to go ahead and apply that model. We're going to say that the amount that we end with, our final amount, is going to be equal to our initial amount, Q0, times Euler's number to the power of our rate, K, times time. And let's just plug in what we know, right? We know that we start off with 6 grams here. We're going to multiply that times Euler's number times the power of our rate times time. Now, we don't really know what the rate is, but we know that time is 1,000 years. So we want to figure out how much is left over after 1,000 years of decay. And so that kind of presents a little bit of an interesting question. You know, like how do we figure out what this is going to be when we don't know what the rate is? Well, the key to that is knowing that this is a half-life problem. And so we know that this is going to be 3 grams that it's going to go ahead and decay into after so long. So 3 grams is what it's going to decay into. We know we started off with 6 grams, and that's going to be times e to the power of 1,000 times k. And so it's going to be by doing this formula and isolating k in this problem that we're going to be able to do this. Now, I actually made a mistake when I wrote this down here because we know that it doesn't take it 1,000 years to decay in half. We know that it takes it 5,730 years to decay in half. And so I shouldn't have written down 1,000 there. I should have written down the 5,730. And so this gives us the ability to go ahead and use some of the tricks that we've been talking about here in this video to isolate k here in this formula. And so when we do that, we're just going to go ahead and start that off by dividing this by 6 on both sides of the equation. On the left-hand side, that reduces down to 1/2, hence the name half-life. And that's equal to e to the power of 5,730 times k. Now again, we're trying to isolate k in this example. And so now that we have this down to an exponential, we can go ahead and convert this to log language to get that k out of the realm of an exponent here. And so we could say log with the base of e, or in other words, natural log of 1/2 is equal to 5,730 times k. And of course, we're trying to isolate k, so we could plug it into our other equation over there. And so to isolate k here, we could just go ahead and simply divide both sides by that 5,730 and then punch that into a calculator and see what that's going to be equal to. So let's go to the calculator here and let's punch that in. So that's going to be the natural log of the fraction 1/2 over 5,730. And if we punch that in and press enter, you can see that the calculator gives us this result in scientific notation. That's what that capital letter E stands for. We've talked about that sort of thing before. That means that this number is so small that the calculator is going to have to represent it in this way. And if we wanted to figure out what number this exactly is equal to, we would just move that decimal point to the left 4 spaces and fill in those spaces with zeros, and that would be the actual number that this corresponds to. We don't really need to write down what that number is because we know what that number is going to be needed for. We know that whatever k is down here, we know that we're just going to have to take it and plug it back in up here into this equation. And so what we're going to go ahead and do is basically just go ahead and use the feature of our T84 that allows us to do a calculation with our previous answer, and we're going to get our result pretty immediately here. So we know that we need to take 6 times Euler's number to the power of 1,000 times our previous answer, and that's going to be the answer to the overall problem here. So 6 times Euler's number to the power of 1,000 times our previous answer. And to pull that up in the T84, we just want to press second negative button. And that puts in ANS. That means the previous answer from our calculator, or in other words, that calculation that we just performed. And if we press enter, the calculator does all the heavy lifting. There's no need for us to round as we go. We get this nice result right here, which is going to be about 5.3. And that is going to be the number of grams that's going to be left over after 1,000 years have passed. Okay, and it makes sense that it would be down to this amount because remember, if we let 5,730 years pass, then our amount of isotope is going to decay to exactly half, so it's going to decay down to 3. If we don't go the full 5,730 years, if we just go 1,000 years, we wouldn't expect it to be anywhere close to half. So it makes sense that starting with 6, we would decay down to about 5.3 grams after only 1,000 years have passed in an example like this. And so that's all I wanted to go ahead and demonstrate here in this video about how to do problems involving exponentials and logarithms and that kind of thing. So hopefully everything makes sense. If not, feel free to send me a message and let me know. And that's all I have for this video. So thank you very much, and I will speak to you guys in the next one.